Okay, folks, let's work through test 4 real quick. Just trying to show you how to go about doing this. All the useful information that we'll need here. Periodic table in case we need it. We got our Avogadro's number, how to turn Celsius and Kelvin. Whole bunch of equations, including ideal gas equations and some conversions into pressures and our R. Okay, let's get started. The stoichiometry equation. How many grams of sodium bicarbonate I need to neutralize 25 mils of 6 molar acid? So we're going from molarity to moles to moles to grams. To go to moles, molarity times volume will give us moles. So 6 molar times 25 mils in liters, 0.025 liters. And then for every 1 mole of acid, you need 1 mole of sodium bicarbonate. And the molar mass of sodium bicarbonate, 23 plus 1 plus 12 plus 16 times 3 is 48. 48 plus, that's 60 plus 24, so I do believe 84 grams. So we're doing this. Should be 12.6 grams. Pulled all those numbers from the periodic table. How many moles of gas would be contained at 1 liter at STP, which means 1 atmosphere, and 273 Kelvin? So there's our T, there's our P. PV equals nRT. Rearranging that, so PV over RT equals N. So 1 times 1 divided by R and 273. R 0.08206. Not much. 0.0446, which runs to 0.045. 3. How much heat must be absorbed by 20 grams of tin mass? Heat capacity of this are 2 temperatures. Q equals MC delta T. 20 times 0.228 times the difference between 232 and 25. You get 943.9, which rounds to 944 joules. Moving right along. Oh, volume of 2 molar HCl is there's an M1 needed to neutralize a V2 of this concentration of KOH. We want to know what is the volume of that. So M1 V1 equals M2 V2, rearranging it. V1 equals 35 times 1.73 divided by 2.0. You get like 30.275, which rounds to 30.3. How much faster would argon if used compared to chlorine? Key thing here is the Cl2. The equation is rate of argon or rate of chlorine equals the square root of the molar mass of chlorine over the molar mass of argon. So the square root, chlorine, 35.5, goes to 70.9. Argon is about 40. So square root of 70.9 divided by 40, 1.33135, about 1.33. So answer C. What is the enthalpy of the following reaction? Enthalpy of the reaction delta H is going to be the sum of the H of the products minus the sum of the H of the reactants. So we need to figure out all of our products. All of our products, negative 127 times 2 because that, and negative 881.7 minus our reactants, AgNO3, negative 313 times 2 because there's 2 of them, and MgCl, 801. So products minus reactants, when you minus a negative, it's the same as adding a positive. You get positive 291.6. Positive 291.6. Here's a Hess's law problem. Hess's law is, what way do we manipulate these two equations to get that equation? Well, I look here, I have this matches. Yeah, so I want to use this equation as given. So just times 1. But this guy is the opposite side. So I want to reverse this equation, and then I'm going to add them up. So negative 60.37 plus a positive 55.8 would give us a negative 4.57. Moving right along. In glass making, sodium carbonate is used to create flux, the sodium oxide. How much sodium carbonate would you need to generate 75 grams of sodium oxide? Grams to moles to moles to grams. We're going to go grams to moles to moles to grams. Pretty easy. Pretty easy. So starting from 75 grams of sodium oxide. 20. Sodium is 23 times 2 is 46 plus 16. 46 plus 16, 50, 60, 62 grams per 1 mole. For every 1 mole of sodium oxide, you get you need 1 mole of sodium carbonate. So 62, carbon is 12, another 2 oxygens is 32, so we're adding 44 onto that. So we add 44. That becomes 10 in 1 mole. You have 106 grams. Gives you about 128.2, which rounds to 128. I know I'm going through it fast. I know, but you can watch it and pause it and reason out for yourself. In the combustion of 100 grams of glucose with 100 grams of oxygen, which is a limiting reagent. So right off the bat, can't be those guys. Those are products. Limiting reagents means reactant. So how much glucose would 100 grams of oxygen react with? I'm turning grams of oxygen to grams of glucose. 100 grams of oxygen. Oxygen is 32 grams in 1 mole. For every 6 moles of oxygen, we need 1 mole of glucose. And glucose, C6, so 12 times 6, 12 times 1, and 6 times 16. It's 180 grams per mole. So how much glucose is needed to fully react 32 grams of oxygen? You need 93.75 grams of glucose, meaning glucose at 100 grams is in excess. So what is the limiting? It must be oxygen. Not the most straightforward or easiest problem because of how it's worded, but not too bad. What is the pressure in bars that would be generated by 5 moles of ideal gas at 280, so we're going to 1.5 liter container. So P equals nRT over V. I'll rewrite that. So P, so we have 5 moles times R 0.08314 times 280 divided by 1.50. Pressure would be something close to 77.597, which rounds to 77.6. So answer A. Planet Venus has an atmosphere of 93 bars. So P total of 93 bars. Contains 96.5% CO2. What is the rest of the gas? With the rest of the gas being essentially N2. What's the partial pressure of nitrogen on Venus? So 100% is equal to 96.5 plus the pressure of the mole fraction of nitrogen. 96.5. So if we calculate that out, it should be 3.5% nitrogen. So to calculate this, P of nitrogen is going to be P total times percent nitrogen. So 93 times 0.035. And it gets on like 3.26 bars. Easy enough. Okay, after 85 grams of a metal absorbs 1,500 joules of heat, it warms from 10 degrees to 55.8, so delta T. What is the heat capacity of the metal? So rearranging the Q equals MC delta T, so have Q divided by M delta T equals C. So 1,500 divided by 85, and the difference between 55.8 and 10 is 45.8. Get 0.3853, which runs to 0.385. If 117 grams of CaCO3 is dissolved in enough water to make 2.5 liters, what is the molarity? So we're going from grams to moles to molarity. 117 grams. Calcium is close to 40. 40 plus 12 plus 48. It's on like 100 grams in 1 mole. And then to get from moles to molarity, we have to divide by volume. Molarity is moles divided by volume. So divided by 2.5 liters. 0.468 molar. Answer C. If gas has a pressure of 720 torr at 250, what would be the pressure at 180? Here's a P1, a V1, a V2. And I want to know P2. So P1 V1 equals P2 V2. So 720 times 250 divided by 180 equals my P2. Something like 1,000 torr. Answer D. Moving right along. What is the percent yield if you use using 480 grams of iron oxide and excess coal and oxygen to produce 300 grams of iron? So we're going to go grams to moles to grams. So starting with 480 grams of iron oxide. So iron, I'm making assumption 56 plus 3 oxygen, so plus 48. So it sounds like 160 grams per 1 mole. For every 2 moles of iron oxide, we produce 4 moles of iron. And as I said, made the assumption for iron, 56. How much should we get? We should get something like 336 grams. Percent yield is actual divided by theoretical times 100. Well, the actual is given. The theoretical, we just calculated. So 300 divided by 336 is 89.285%, which is 89.3. What is the density of 1 atmosphere of air with this molar mass at 9 degrees? So we add 273, which makes this 282 Kelvin. Density, density equals P times molar mass divided by RT. So density is 1 times 28.97 divided by R, 8206 times 282. So do that, you get something like I goofed up. Okay. There we go. 1.25. 2518, which rounds to 1.25. Finally, what is the enthalpy of hydrogen gas? Enthalpy for element, for any element, must equal 0. Because to form an element in the enthalpy of formation, it's from its natural state. So delta H of formation for hydrogen, the reaction is going from hydrogen gas to hydrogen gas. No change would be done. No change is done. There can't be a change in enthalpy. Thus, enthalpy must be 0. That's the only enthalpy I can ever expect you to know. Enthalpy of 0. Every other one, too much. Just a simple setup problem. You don't even have to solve it, but turning grams to moles to moles to grams. 37 grams of methane. Methane, 12 plus 4 is 16 grams of methane for 1 mole of methane. Based on the balanced chemical equation, for every 1 mole of methane, 2 moles of oxygen. And for every 1 mole of oxygen, that weighs 32 grams. That's what I expected them to do. That's all. Nothing more, nothing less. You didn't have to solve it, but if you chose to solve it, you got 148 grams. Okay. Last 2. Considering the van der Waals equation, would a large attractive molecular force A result in larger or smaller pressure? Since this is a minus, as this goes up, the pressure has to go down. Since it's a negative A, as A goes up, pressure must go down if everything's the same. Think of it. More attraction means less collision. And finally, a poor question on my part, but it was supposed to be an easy gimme. A particularly wordy professor is blathering on during lecture, turning oxygen into carbon dioxide under 1 bar of pressure via the following equation. So 6 oxygen is turning into 6 CO2 and solids and liquids. If work is traditionally defined as a pressure times a change in volume, Approximately how much work is the professor doing? There's no change in volume. When delta V is 0, the work is 0. The joke was supposed to be the professor does no work. Sure, he's lecturing, but he's doing no work. It's a force applied over distance. If there's no distance moved, there's no work done. All these numbers were made up out of thin air, but unfortunately this one went right over some people's heads. Sorry for that, but that's what it was. That is the test. Hopefully that will be helpful for you.